challenge. We're going to go over logistic regression in this project. So it's basically establishing the relationship between the dependent variable and one or more independent variables by estimating probabilities using an equation, which is logistic regression. We see NumPy, Matplotlib, Seaborn, Pandas. We see the specific style for ggplot, PyLab with RC parameters. So the data is loaded. It's DMV test data. There's visualizations that are done with the data. Shows passed and failed results for test 2 scores. There's a logistic sigmoid function which was defined. So this function is defined here with returning 1 over 1 plus the exponential of negative x, and then logistic function defined. There's a cost function and a gradient. So this is the length of y, this theta xy. Logistic function uses np dot with x theta, and there's an error function cost gradient. I think we saw this before. We can see mean scores, standard deviation scores, scores minus mean scores over standard deviation scores. It's printing out rows and columns, appending the NumPy here, reshaping values, doing theta initialization, having cost gradient, and then there's gradient descent with the for loop and the theta. And this graph is plotted with convergence. There's a decision boundary as well between the passed and fail results with the scatter plot over here. There's two different scatter plots. One is AX and one is this scatter plot over here. This one, AX is set with test 1 scores and test 2 scores the Y label. There's a legend, 2 boundaries. It's basically trying to draw a line in between, I guess, which is maybe the average. That's it for that notebook. Principal component analysis is pretty important. It's a dimensionality reduction technique used to reduce dimensionality of large data sets to smaller ones. You transform a large set of variables while preserving the information all along. We basically use these 4 libraries which you've seen before, and there's sklearn preprocessing with standard scalar. Data is loaded. It's iris data, which is common data set with plant data. There's a scatter plot. There's eigenvectors and eigenvalues, which are used in linear algebra. Our covariance matrix is set up with these eigenvalues and eigenvectors, and it's just printing those out here. There's singular value decomposition, which I don't really know what this does or why we have it, but it looks like it's making an array. Then principal components are defined, and it's telling us how many components there are. And then there's data that's plotted. It's trying to put up clusters, and then you kind of just go from there. And then we have this last notebook here, which is Advanced Regression Part 2. This one has much more libraries. These 4 we've seen. CM is there, the color library is there. We have pipeline, and we have preprocessing with standard scalar. We have a cross-validation score, and we have metrics. And we have CMAP. The data is loaded here. Features are declared for X and Y. We have the XY features listed, split into the train and test data. Rescale the data with cross-validation and valuation metrics. You have a cross-validation function here, and evaluate the mean squared error, root mean square, mean absolute error, and R squared. And we have linear regression. Import this module, normalize it, fit it, have test predictions, print the train test values, and have all the statistics shown. This is probably single vector machine regression. So this SVM is imported and imports the single vector regression from that library. There's a single vector machine regression model with this kernel, and you train the X train Y data. You have test predictions and train predictions, and you do a train set evaluation and test set evaluation. And random forest regression we've seen this before, so that's imported. There's a new model, and you can compare all these metrics and see the size of error. The R square is high for the train set and a bit lower for a test set, which makes sense. And there's also SGD regressors, so now it's just cross-validating and checking different models. Elastic net is another model, lasso regression, ridge regression. So it's basically comparing and checking these models. So that's pretty much it. All these models are useful for advanced regression techniques, and they can be used to develop projects. Thanks for listening.